Hello everyone, myself Sandeep Bhad, Assistant Professor, Department of Electronics and Telecommunication, Roonta College of Engineering and Technology, Bhilai, affiliated to CSVTU Bhilai. Welcome you course on Fundamental of Communication and its application. Today's our topic of discussion is phase shift keying, that is a part of digital communication. Hope you have learned about the digital modulation techniques, ASK, FSK in previous lectures. We have a course content like this. The first one we will go through the objective of the lecture, introduction to the digital modulation, phase shift keying, and we will also see the generation and reception of the PSK systems, and last one is the spectrum of the PSK system. Apart from this, we also see the bandwidth for PSK, drawbacks and merits, and the application of PSK. Now, let us come with the what are the objectives of this lecture. When we have these lectures, after that lecture you will be able to see that you will having the clear idea about the basic idea of digital modulation techniques, basic principle of PSK modulation, generation and reception of PSK systems, and some few performance parameters that we will see on later, right. So, these are the objectives of our today's lectures. Let us come with the what exactly digital modulation and what exactly the PSK system. Before dealing with PSK systems, one should know something about what exactly digital scheme. The digital scheme and how it is differ from analog and why it is the what we say as a famous. The digital modulation is a process where digital information is transmitted over an analog carrier waves by varying the carrier amplitude, frequency or phase according to the digital signals. The primary goal of digital modulation is to convert digital data into a form suitable for transmission or communication channel such as radio, television or wire network. The most common type of digital modulation techniques includes amplitude shift keying, that is nothing but ASK. The second one is a PSK, phase shift keying, and frequency shift keying, and one more is there, that is quadrature amplitude modulation QAM. So, these are the digital modulation techniques. In the form of analog modulation, on the other hand, is the techniques where analog signals continuous in nature are transmitted over an analog carrier by modifying the carrier amplitude, frequency or phase according to the analog signals. It is commonly used in a radio broadcasting, television and other communication system. For example, analog modulation includes the AM modulation, that is amplitude modulation, and one is the frequency modulation, that is FM. Now, let us see what are the key differences between analog and digital modulation techniques. Simply, if we see the signal type in analog modulation that transmit continuous signal, it can represent an infinite number of values within a given range. In digital modulation, they transmit discrete signal in the form of binary data, that is 0 and 1. Second things, the key parameter is why it is differ, that is we come with the complexity. In analog modulation, it is simpler in design and required less bandwidth. What about digital? In digital modulation, it is more complex due to encoding and decoding process, but it offers the better noise immunity and data integrity. What about the noise sensitivity in analog system? Analog system, where you will find it is more susceptible to the noise and distortion, leading to degradation of quality signal. What about digital? In digital, you will find it is less affected by noise, as digital signals can be generated and error corrected. And what about the data compression and encryption? In analog modulation, you will find there is a very limited capability for data compression and encryption. In digital modulation, it supports data compression, encryption and enhancing the data security and efficiency. So, you will find here the key differences between analog and digital system. Now, take an example. Nowadays, you are using the social media applications, all the 4G, 5G systems, the television systems are there, satellite systems are there, you have a Bluetooth devices, wearable devices and some smart home applications, IoT devices, where you will find the digital modulation and digital scheme. Without this, we cannot have the much more data capacity that we use and having the secured system. So, this is what about the why we go for digital modulation as compared to analog and the key differences. Now, let us discuss about the main objective of this lecture, that is phase shift keying. If you see, shift keying is nothing but that is alteration of changes in 0 and 1, right. So, in digital modulation techniques used to convey data by alternating specific attributes of carrier signal such as its amplitude, frequency or phase, that is switching between 1 and zeros. Phase shift keying is most efficient modulation techniques as it is used for high data rate. So, it is knownly for high data rate system where we needs. In PSK, phase of the sinusoidal carrier is changed according to the data bits to be transmitted. Also, a bipolar NRZ signal is used to represent the digital data coming from the digital sources. Here we have the whatever data we want to transmit, that should be represented in a NRZ format. Now, what exactly NRZ? NRZ is nothing but the non return to 0 format. It means having the polarity of, that is bipolar means having the polarity of plus and minus, right, that is peak to peak signal and represented with the NRZ. Now, let us talk about the what is the basic principle of phase shift keying, on what principle it is depend. So, if you see here, there are three main things, that is the phase shifting, that is the switching of the signal between 0 and 1, the carrier will be get switches as compared to the 0 and 1 signals that we use applying. Second one is the coherent detection, that is the second thing that is important in the digital PSK system. There are two types of signal exactly, the coherent and non coherent, but we are discussing here only coherent detections, that receiver should detect the coherent detection. And the third one is the concept of this PSK system is signal constellation. Here the different phases shapes are represented, the what signal constellation, even we have a diagram for the signal constellation, we can plot, that is not an issue. In phase shift keying, the binary symbol 1 and 0 modulate the phase of the carrier. Suppose let the carrier, we have a carrier signal and we can that signal will be represented with the S of t equal to a cos of 2 pi f t, right. Here the a cos means a is representing the peak value of sinusoidal carrier, that is nothing but always the amplitude of the carrier, right. So, the power dissipations will be, if you take this signal, the power dissipation will be half of the square, the a is the, it represents the peak value. So, if you want the what exactly the peak value, a equal to the root under root of 2 p, right. When the symbol is changed, then the phase of the carrier is also changed by 180 degree, that is we call as a 180 means pi radians, right. Now, for that we need to take a consider the symbol variations. For symbol 1, that is we can say as S 1 of t equal to under root 2 p cos of 2 pi f 0 of t, and for symbol 0, that is we can say as S of 2 t is under root 2 p cos of 2 pi f t plus pi. Pi is nothing but that is the shifting of or change in a phase, that is we already discussed 180 degree. As we can write this S of 2 t in another way also. What is the way is that S of t equal to minus of under root 2 p cos of 2 pi f 0 of t. So, this minus sign indicate the change in the phase. Now, if you see the figure number 2 in our slide presentation, you check that figure. Now, it shows that a binary signal and its equivalent of signal. So, there are two parts in this figure. The figure number 2, A is the part, that A you will having the only the binary sequence, the what sequence we are applying 1 0 1 1 0 1, this would be the sequence, and the B part is the what we say as equivalent signal of BT, that is a NRZ. NRZ means non return to 0 and it is a bipolar signal. So, we are represent this binary signal in a two way, that is the bipolar way, that is the plus 1 and minus 1. So, you can check here the figure number 2, you will be able to see that the binary sequence will be converted into the NRZ signal. So, NRZ means not equal to 0, the signal will be as it is whatever we are applying. As from the signal that bipolar signal, it is directly modulated carrier. That what is our carrier? Our carrier is cos of 2 pi f of t. This is our carrier, and this carrier will be modulated as compared with the whatever the data bits we applied input, right. Now, let us talk about the how to generate the PSK signal. That is, there is a main role of PSK modulator here. Here we required kind of inputs. What input we need? We need a binary data sequence, that is in terms of 1 and 0. The modulator, second one is modulator and carrier. You can see the figure number 3 in presentation, where you will find the PSK generator. PSK generator consists of the binary data sequence, bipolar NRZ level encoder, the first block, and the output of this NRZ will be fed to the balance modulator, and this balance modulator having the another signal, that is carrier signal. So, here you will find the modulation process. Once we get the bipolar NRZ signal in the product with the carrier signal, you will have the PSK signal, right. So, this is what the generation of PSK signal. Here you will find the phase shift keying modulated signal. The PSK signal can be generated by applying carrier signal to the balance modulator, and this balance modulator is B of t is applied as a modulating signal to the balance modulator. So, in this figure, this is clear that the NRZ will be converted into the bit of sequence, and that bit of sequence will be produced, and finally, we will get the PSK signal, right. Now, once we transmitted this signal through any channel, maybe wire, wireless, or there are two types of channel only, the wire channel having directly and wireless having there are different ways. Another channel we have a that is in terms of light, that is we call it fiber, right. So, there is no issue of what kind of channel we using while transmitting, but at the reception how to receive this PSK signal. So, for the reception of PSK signal, again if you check the figure number 4 in our presentation, you will find here there are few blocks. So, the blocks are we have a square law devices there, second one is a band pass filter, third one is a frequency divider, that is by 2. One more block is there, that is synchronous demodulator, that is we call as a multiplier, then bit synchronizer and integrator. So, let us talk about what are those the basic functional blocks are there, and how they will receive the signal and process, and how we will get the exactly what we transmitted to signal at the end of this module the reception or receiver, right. So, you can having the signal from channel, that is PSK signal, we fed it into the square law device. The square law device will having another signal, it will provide, that is cos square of 2 pi f c t plus theta. Here you will find some changes in a signal, and then this signal will be fed to the band pass filter. So, band pass means why? In a band pass filter you will find here the complete, there is a set of bands in between this frequency it will pass, right. The band pass filter will also give you the output of this band pass filter will be cos 2 of f of c t plus theta. So, theta will be, that is the radian, the what changes will be there after the change in a phase, right. So, same will be applied to the frequency divided by 2. Here you will find there is a division of frequency by 2, and this is must, and it will be given to, it will having the equation you can find here cos of 2 pi f c t plus theta. This signal will be given to the synchronous demodulator, that is we call as a multiplier. At the same time, the multiplier also having for the synchronization purpose input signal, that is the PSK signal in comparison with the frequency divider signal. Here you will find there is a synchronization purpose, the what input was there and as compared to input what are the changes at the output. So, again you will find here the once we get the synchronous signal multiplication, after multiplication you will find the b of t under root 2 p cos square 2 pi f b t minus t plus theta, right. So, this signal will be given to the integrator. At the same time we also have a bit synchronizer. That bit synchronizer will having the switching between S1 and S2. So, it will take a decision ki what time the S1 will be get switched and what time S2 will be get switched, right. So, that switching completely depends on the decision module that is given by the synchronous demodulator, right, multiplier, right. So, you will find here the input signal is given to the bit synchronizer and the integrator. What is the function of integrator? Integrator will integrate the all signal right from the duration 0 to T1, T2 to T3, T4 like that, right. Every duration of bit duration will be integrated at the output, and as compared to the switchings, there will be, you will find the integrator function will be work and the output function will be work. So, in the block diagram what we discuss here, it is used for to recover the baseband signal from PSK signal. So, this is the main function of the receiver is how to recover the baseband signal. Suppose in a daily life we know very well you are listening FM systems. So, FM is what exactly? FM is a demodulator. So, exactly whatever you are listening from the FM signal, so it will be demodulated at the receiver. Same function you will find here in PSK, but in terms of the digital. Here we are talking about the digital system, the input bits are in terms of 1 and zeros. So, whatever transmitted PSK signal we already discussed, the B of t under root 2 p cos 2 pi f of t, this would be, this signal would undergoes to the phase changing depending upon the time delay from transmitter to receiver, because while transmission of the signal there is a time delay. This phase change is normally fixed phase, right, in transmitting the signal. Now, let us, the phase shift will be theta, and we assume that there is a theta phase shift, whatever changes from at the time of the sequence bit 1 and 0, there will be change in a theta. So, therefore, the signal at the input of the receiver is the S of t equal to B of t under root 2 p cos of 2 pi f of t plus theta. Right. Now, from this received signal, carrier is separated since this is coherent, right. In figure we have given that this is the coherent signal. The received signal is passed through square law detection. As the square law detector you can find in the block diagram, that is the first block is shown, that is the square law detector. At the output of the square law detector, the device, its signal gives you cos square 2 pi f of t plus theta, right. So, here you will find cos square. Now, note here that we have neglected the amplitude, right. You will not find it in the A, as we are transmitting the A, but you will not finding A amplitude, right. We are neglecting here amplitude A, because we are only interested in the carrier of the signal, right. So, we know that the cos square theta equal to 1 plus cos of 2 theta by 2, right. The cos square 2 pi f of t plus theta equal to 1 plus cos square 2 pi f of t plus theta by 2, or we can write in another way, that is half plus half of the cos square 2 pi f of t plus theta. Here the half represent the DC level, right. So, this signal is the pass through band pass filter, whose pass band is exactly, you will find center means 2 f of 0, right. The baseband signal removes this DC level, that is half of, right, and its output will be get cos square 2 pi f of t plus theta. So, this is the required output after removing the DC level, right. Now, this signal is frequency of 2 of 0, it means the frequency of the signal is twice of f 0, right. Hence, it is passed through frequency divider by 2. So, there are two frequencies, that is why we need to divide by the frequency by 2 divider, right. This is one of the block you can see in a figure. We get the carrier signal whose frequency is f 0, that means cos of 2 pi f of t plus theta. The synchronous, or we may say as a coherent demodulator, multiplies the input signal and the record carrier, right. Therefore, at the output of the multiplier we get B of t under root 2 p cos of 2 pi f of t plus theta and into cos of 2 pi f of t plus theta, that can be given equal to B of t under root 2 p cos square 2 pi f of t plus theta, or B of t under root 2 p divided by 2 1 plus cos square 2 pi f of 0 t plus theta. This signal is applied to the bit synchronizer and integrator at the same time. To the synchronizer having the different role and the integrator having a different role. The bit synchronizer take care of starting and ending time of the bit. Once the bit gets started and the end, so that care will be taken by the bit synchronizer, it will synchronize with the bit. And at the end of bit duration, that is t duration, the bit synchronizer integrator integrates closest switch of S, right. So, that is done by the temporary only. So, that switch will be closed temporarily once the bit duration gets started and ended. This contains the output of an integrator to the decision device, right. So, decision device is connected over there and the output is given to this device. It is equivalent to the open switch S2 also having the sampling, the output of the integrator. So, there are two switches S1 and S2. S2 is having a sampling switch, right. The synchronizer then switch S1 is closed temporarily. Once there is a two switches S1 and S2, one is open, one is closed, right. This is continuously shifting, right. So, this resets the 0. The integrator integrates next bit. Let us reset the integrator voltage, that is the integral number of cycles are there, and integrate all those duration from T1, T2, T3, or TB1, TB2, TB2, TB3, TB4 likewise integrate all the cycles or all the carriers as per the different bits, right. So, this is a phase change occur in the carrier only at the 0 crossing. So, you will find in a slide number 13, the figure number 5, you can check over there. We have a PSK waveform, whatever PSK waveform we get from the complete system. So, there is at the time of 0, at the time of 1, means what is exactly happening at the 1 bit 1 and what is exactly happening at the bit 0. Definitely, you can clear from this system or cycle whatever sinusoidal we are applying or giving here. Whenever you are having the change in a phase or change in a bit, the phase gets changes with the 180 degree, right. You can see here the first bit having the complete carrier, and just changing the bit come to the 0, the phase gets changes with the 180 degree. Even we have a second signal, that is 1 1, you will find there is no change in the carrier wave. Once you get the change in the phase or change in a bit, you will find change in a phase. So, this can be seen from this figure number 5, right. So, this is about the PSK waveform. Now, this is completely about the, as of now we have learned about, we talk about the basic concept of digital modulation. Second one is the generation of the PSK, detection of the PSK. Now, there are few performance metric parameters, right. So, the performance metric parameters are this: we have a spectrum of the PSK signal. Now, we know that the waveform B of t is NRZ, bipolar NRZ, right. So, in this waveform there are rectangular pulses or amplitude of peak to peak amplitude, that is plus minus V, right. If we say that each pulse is plus minus Tb by 2 around its center, then it becomes easy to find Fourier transformation of each pulses, right. Now, let us consider this power spectral density of PSK signal. The figure that clearly shows that there are two lobes, one at f0 and another as minus f0. The same spectrum of figure 4 is placed at plus f0 and minus f0, but the amplitude of main lobe, that is Pt by 2 in figure you can check here, and thus they are reduced to half. The spectrum of the PSK, that is S of f, as well as the binary PSK extend over the all frequencies. You can see the figure of that spread spectrum of the system. Here you will find that figure will be available in the slide figure number 5. Now, let us talk about something about the bandwidth of PSK. The spectrum of PSK signal is generated or centered around the set carrier frequency f0 if f of b equal to 1 by T b, then for PSK maximum frequency in the baseband signal will be f 0. From figure number 4, it would be f 0 minus f b to f 0 plus f b. Therefore, bandwidth of PSK signal is bandwidth equal to highest frequency minus lowest frequency in the main lobe, that is bandwidth equal to f 0 plus f b minus f 0 minus f b. So, it obviously we having a bandwidth of twice of f b. BPSK transmit 1 bit per symbol, meaning the symbol rate is equal to the bit rate. Minimum bandwidth of BPSK, or may say as a PSK signal, is equal to twice of the highest frequency contained in the baseband signal. The bandwidth of PSK signal is influenced by the data rate and pulse shaping used in the transmission. This is all about the performance parameter of PSK. Now, let us discuss something about the what are the drawback of PSK system. The PSK system is widely used modulation techniques due to its simplicity and robustness. However, it does not have several drawbacks. Having few drawbacks, we are having discussed one by one. The first one is low bandwidth efficiency, second one is low data rate, third one is the susceptibility of phase ambiguity, fourth one poor performance in multipath environment, then sensitivity to noise, single bit per symbol limitation, complex receiver design. So, these all are 7 the drawbacks, these are the key drawbacks. If you see the key parameters or key what we say as the drawback of PSK system is, that is ambiguity in output signal. You can see the figure number 4, it shows the block diagram of PSK receiver, and it is a generation of the carrier in the receiver. Now, we start by squaring the b of t, that is under root 2 p cos of 2 pi f of t plus theta, and if the signal received signal is minus b of t under root 2 p cos of 2 pi f of t plus theta, then the squared signal remain same as therefore. Therefore, the record carrier is unchanged even if the input signal has changed its sign, right. So, we have a plus and minus sign there. So, here you cannot differentiate what was the sign or signal between or signal before, whether it is sign plus or minus or signal 1 or 0. So, therefore, it is not possible to determine whether the received signal is equal to b of t or minus b of t. This result in ambiguity in the output signal. This problem can be removed if we use a differential phase shift keying, that is DPSK. Now, this is what about the complete drawbacks of the PSK system. Apart from this PSK, we have a different forms of PSK system. There are 3 types of systems. The first one is a differential phase shift keying, nothing but a DPSK. Second one is a differentially encoded PSK, DEPSK, and third one is the quadrature phase shift keying, QPSK. Application of, now let us talk about the few applications of PSK system. There are several applications of PSK. Some key applications of PSK are, now you know very well, you have a smart watches, indoor so many systems are there, 4G system, 5G systems are there, the what we say as embedded systems are there. Everywhere you will find, where you will find the IoT systems and there, right, where you will find, everywhere you will find such kind of digital modulation techniques. The PSK you will find most of the systems. The first application of PSK is the Wi-Fi communication. PSK is used in wireless LAN technologies, particularly exactly IEEE 802.11 standard. It helps achieving the robust communication by providing good bandwidth efficiency and noise reliance, right. This is the most important application in Wi-Fi system. The second application of the PSK is satellite communication. PSK is employed in satellite communication for data transmission between ground station and satellite. Its ability to handle various frequencies band make it suitable for the applications. The next application of PSK is radio frequency identification, that is RFID. PSK modulator is used in RFID system to encode the data, which is then transmitted between RFID tags and readers. This provides efficient means to tracking and identification. The next application of PSK is digital television broadcasting. PSK play a crucial role in digital TV by enabling efficient video and audio transmission. This ensures the high quality of broadcast with minimum interference. The next application is cellular network. PSK is also used in mobile communication network such as GSM, 3G, 4G, LTE to enhance the data transmission rate and spectral efficiency. It provides a better data integrity and speed. The optimal communication systems, PSK is applied in a what we say as a fiber optic communications, where you will find the long distance communication that PSK will use. Now, let us conclude this lecture. We have discussed about the basic digital systems, their advantage, disadvantage. Even we discuss the how it is differ from the analog system and other systems. The PSK is widely used digital modulation techniques, where phase of the carrier is changed to represent digital data. It is favored in communication system due to its robustness against noise and efficient use of bandwidth. PSK can be implemented in various forms such as binary PSK, QPSK and DPSK. The other higher order also can possible with this PSK system. It is offering the different trade-offs between complexity and data rate. This is what about the PSK. Thank you for listening the lectures.